the starting point for forming our 3D robots is this multi-layer, sequence of fabrication steps. But what's unique, I guess, in what we're doing here is that we can take those planar multi-layer architectures, we can release them as thin films, essentially, from thin structured films from the underlying supporting substrate. And then we can buckle them in a controlled manner to move those 2D collections of materials into the third dimension. And that's kind of a critical aspect. I guess it's difficult to build a robot that's just perfectly planar in 2D in its geometry. You think about, insect life maybe as an inspiration for microscale robots. They all involve, complex 3D articulations and architectures. And so being able to move those patterned thin film materials out of the plane up into the third dimension is critically important. And the technique that we use to do that, is similar conceptually to a children's pop-up book, in a sense, that we're controlling buckling deformations that irreversibly then move those 2D structures into 3D architectures. And so that's how we form robots that resemble crickets and inchworms and crabs and all kinds of other structures where the legs move out in a direction orthogonal to the plane of the body of the robot. So that's kind of one feature of
In this podcast, I'm sharing my passion and curiosity for soft robotics, where we share inspiring stories about the work we do and how we can push the limit. I am Mara Dwini, and this is Soft Robotics Podcast. Support for this show comes from Science Robotics Journal. I really find Science Robotics to be a great resource for reliable and tangible research where we can really push the limit of the science we do in robotics. Great way to stay up to date with the published article is checking out the released monthly issue. All the links will be included in each episode description. We will also happen to have a regular conversation on the most published science robotic articles, where also you can contribute with your question and thoughts about the research. Thanks Science Robotics for sponsoring Soft Robotics Podcast.
And maybe I would like to ask you first, how do you see the material and architecture, if we speak about in the material level, and Thinsis paper is focusing on the small scale? How do you see the combination of material and architecture in the design in different scales?
Yeah, I think that's a good question. So I guess any sort of robotic system relies on a specific architecture for the overall device construct, but also embedding various functional materials in layouts that achieve a certain engineering goal and allows one to satisfy requirements. So I guess our robots are no different in that sense. The focus for us is on very small scale robots as just kind of an exploratory academic level effort, but one in which successful outcomes may have implications for how we think about minimally invasive surgeries, for example, in the future. So small scale was an important attribute in the devices that we've reported in this paper. The other feature is an ability to locomote on solid surfaces in open air. So there are quite a few sort of micro robots that are designed to swim in liquids, and I think that work is great. It's very interesting. I think far fewer examples, however, exist of sub-millimeter scale robots that are able to walk on solid surfaces, in open air, as I mentioned before. So those are our two goals, I guess, is to develop a set of fabrication schemes and design architectures and functional materials that would allow us to build very tiny walking robots that we could control remotely.
Mm-hmm. So I think it's interesting also to mention that having heterogeneous material and plus the architecture. In that sense, which one is significant when it comes to tackling this problem? If you speak at a smaller scale, you need to get this feature, for example. Which one do you think was leveraging the possibilities that can do different modes of locomotion? Is it significantly in architecture or using heterogeneous material? If you can elaborate on that.
Yeah, well, probably both. They sort of go hand in hand. There's strong synergies there, I guess. I feel like the main advances in this latest paper, from our group are in techniques for forming very tiny 3D structures in ways that align with the kind of thin film growth, etching, and photolithographic patterning techniques that are developed from the semiconductor industry. So, the process really begins with those kinds of techniques in microfabrication. A sequence of deposition of thin films, patterning of those films, in a repetitive cycle to create complex multi-material, multi-layer structures that have the necessary geometries. So you think about the way an integrated circuit is built. It's very much similar to the way that we start the fabrication of our 3D microscale robots. That turns out to be very powerful because we can leverage all of the technologies and manufacturing approaches that have been developed in the integrated circuit industry, and we can also very naturally integrate then all the various microsystems technologies that can be achieved with those kinds of schemes. So it's really the starting point for forming our 3D robots is this multi-layer sequence of fabrication steps. But what's unique, I guess, in what we're doing here is that we can take those planar multi-layer architectures, we can release them as thin films, essentially, from thin structured films from the underlying supporting substrate. And then we can buckle them in a controlled manner to move those 2D collections of materials into the third dimension. And that's kind of a critical aspect. I guess it's difficult to build a robot that's just perfectly planar in 2D in its geometry. You think about, insect life maybe as an inspiration for microscale robots. They all involve, complex 3D articulations and architectures. And so being able to move those patterned thin film materials out of the plane up into the third dimension is critically important. And the technique that we use to do that, is similar conceptually to a children's pop-up book in a sense, that we're controlling buckling deformations that irreversibly then move those 2D structures into 3D architectures. And so that's how we form robots that resemble crickets and inchworms and crabs and all kinds of other structures where the legs move out in a direction orthogonal to the plane of the body of the robot. So that's kind of one feature of our work, is the ability to form these very tiny 3D structures out of advanced materials that are patterned with very high resolution and fidelity. So that's one unique aspect of what we're doing relative to other work in micro robotics. The other thing is in the development of kind of a remotely actuated and remotely addressed muscle type structure, which relies on a shape memory alloy, which is sort of an old class of material. But what we've done is we've structured those shape memory alloys into shapes. We've located them at the joints of the limbs of our robots, and then we coat them conformally with a thin layer of glass that provides kind of an elastic restoring force. So local heating will induce a shape change in those alloy materials to their original sort of remembered shape, I guess. And then upon cooling, that thin layer of glass acts as an elastic restoring force to move that shape memory alloy structure back into its deformed geometry. And so that creates like a two-way motion. And by repetitive thermal actuation remotely using a laser and optical absorption to induce that heating, we can create a gate. And so we can actuate different limbs across the body of the robot. And if we do that in sequence, we can cause the robot to walk in different directions. So it's that kind of scheme for actuation and gate coupled with this 3D approach in fabricating tiny sort of sub-millimeter scale structures.
Great. Maybe there's two questions here. The first one about maybe the challenges of multi-material. It seems the multi-material is still quite challenging, maybe in soft robotics, so to speak. And also the design consideration for the architecture in that scale. What may be challenging from the experience in fabrication or the design of the geometry and combining this multi-material in that scale? What the design consideration do you think very significant when you design?
Yeah, well, I think, any robot includes a diverse collection of materials. I'm not sure of any really kind of useful or meaningful robot can be built out of a single material. Maybe there's some certain examples of that, but you're quite limited. And so, I think an ability to bring diverse classes of materials together in sort of a monolithic construct is probably a key requirement of advanced robots for the future, and certainly that also applies, as a consideration around the design of sub-millimeter scale robots. So if you think about, options in patterning and fabricating sub-millimeter scale 3D structures, I think a lot of people would immediately, turn to various techniques in 3D printing, stereolithography, or direct write type printing approaches, and you could go down that path, but I think it's it's quite difficult to embed multiple classes of diverse materials into a single 3D structure using those approaches. They work pretty well if you're interested in a 3D structure made out of a polymer, or maybe a ceramic or metal, but if you want a structure that includes semiconductors and metals and polymers and ceramics all together, patterned relative to one another with great registration and fine spatial resolution, I think you quickly move outside of the realm of options that are supported with 3D printing techniques as they exist today. And so I think our approach is different and valuable in that context because it bypasses those limitations and leverages, as I was mentioning before, the very sophisticated manufacturing techniques that are used for 2D planar structures in the integrated circuit industry and generally the micro electromechanical systems in industry, optoelectronics, all formed using these sorts of layer by layer and high resolution photolithography approaches. We leverage all of that, and so we immediately have as a starting point a very high level of sophistication in materials options, geometries, and so on, and we create the structures, and then the 3D happens as a final step to transform geometrically 2D structures, multi-material structures formed in that kind of way up into the third dimension to realize the kind of architectures that are necessary for kind of realistic insect-inspired, I guess, robots at these scales.
Great. Maybe I want to go for again with stimulus to change the shape of the robot and make an out-of-plan formation here. Have you ever thought about other techniques beyond heating, for example, do you think?
Yeah, I mean, I think we've, presented one possibility, for actuation, and as you point out, it's thermal in the basic mechanism, exploiting this shape memory alloy and this sort of elastically resilient coating on top of it to create this two-way repeatable motion. At these very small scales, thermal is not too bad because the rates of passive cooling are very high because of the large surface area to volume ratio. So you can actually make these robots move pretty quickly, even though the mechanism for actuation is thermal in its origin. So it's not slow in that sense. Maybe not as power efficient as it could be, I guess, as a thermal sort of technique. Maybe power efficiency represents a disadvantage of sorts. I think the way that we're inducing the heating by optical illumination is a reasonable kind of starting point, but it does require optical access, to the robot. So you need to be able to scan a laser across the body of the robot to actuate different of these shape memory alloy based muscles to create the desired movements. And maybe, certain applications would allow for that optical access. In others, I think that maybe creates sort of certain limitations. And so I feel like into the future, there are many other opportunities for different forms of actuation. Maybe they're still thermal in their origin, but perhaps they eliminate this requirement for optical access. And there, I think, for that range of possibilities, as well as other forms of actuators, I think the approach that we've put together for forming the 3D structures, the architectures, are going to be quite compatible with almost any type of material that one could conceive of for the muscles, for the actuators, and also with the very natural ability to embed radio frequency circuitry and other kinds of electronic components directly into the body of the robot, maybe to support other kinds of modes of remote control. So again, I think we're pretty happy with the fabrication route, and as new ideas for actuators emerge, I think they will drop in quite nicely to this scheme for forming the robots. And we put forward one kind of idea, and it sort of works, but it's not perfect, and so I think there's definitely room for improvement there. But like I said, I think the fabrication schemes are going to be well aligned with any material that I can think of, or any actuation scheme that I can think of, will be compatible and easily integrated into these kinds of 3D robot structures that we've formed in this way.
Maybe a quick question. Do you think there's a limitation for any kind of material with architecture when it comes to fabrication? Because I don't know from your experience, if there's any limitation to the architecture?
Yeah, I suppose there are some limitations ultimately. I don't think the limitations are in feature sizes. We could go much smaller, actually, than the robots that we reported. The difficulty, at least in terrestrial robots moving on solid surfaces in air, is that contact forces begin to dominate as the size of the robots continues to decrease. So we went about as small as you can possibly go without, stiction becoming a problem. As you might imagine, just intuitively, as objects get smaller and smaller, those surface forces become larger and larger, thereby demanding stronger and stronger modes of actuation to induce motion. So there's really, in terms of the fabrication scheme, there's really no practical limit that I see in terms of the overall size scales. Like I said, we could go 10 times smaller than what we reported. We just couldn't move the robots once they're that small. They're just sticking to everything. So, but if it's a swimmer, it's not a problem, in that sense, not as significant a problem anyway. So I don't think feature size is going to be a problem. Perhaps certain 3D geometries. I mean, I guess what we're able to do very easily with this scheme is 3D structures that are more or less sort of open architecture in their overall design. If you want, a dense 3D structure that has materials distributed through a volumetric space with little open space, I think that becomes a little bit more difficult. As you might imagine, if you think about a kid's pop-up book, again, everything is starting in the plane, and then you move into the third dimension. You only have a certain amount of materials, and now you're moving them from a multi-layer architecture in a 2D geometry into a 3D geometry. It's kind of intuitive that you would end up with a lot of open space, and so I think that's kind of a feature of the approach. You can use sort of different kinds of multi-layers. You stack up more and more layers in the 2D precursor, and then you can achieve more space-filling 3D structures, but ultimately there will be kind of a limitation there. But at the same time, if you think about insects as an inspiration, I mean, the legs are kind of strung out over space, and so there is a lot of open area there that I think is sort of naturally well aligned to the kinds of 3D structures. But we can't do arbitrary 3D structures, let's say, and in that sense we don't have the same level of versatility as one has in a 3D printer. And I think there's probably also a need for inverse design tools. So we have a good capability for modeling the forward problem. We know for a given 2D precursor what it will move into, during that geometry transformation process. But if you ask me, here's the 3D geometry I want to create, what does my 2D precursor need to look like? That's a much more challenging computational problem. So maybe there's some real opportunity there from a modeling standpoint to develop those kinds of design tools for the future.
That's a good point. Maybe I want to ask you if there is something maybe part of this design was quite challenging. You mentioned computation and modeling, but maybe it was quite challenging in the beginning, or maybe an understanding. And also, if you hold also different views, like disagreement, and if we speak about microrobotic design, maybe you think the approaches may be used commonly in this field, you have a different views. You think maybe that's not the right approach, critique or different views.
Yeah, I mean, I think design tools are going to be important, as, in any field of engineering, you want to be able to do upfront design and modeling. And like I said, we have a fairly powerful framework, that allows us to predict, the forward problem. And this is in collaboration with Professor Yonggang Huang, who's in mechanical engineering here. He does all the simulations for us, actually. So I think that's pretty well developed, and we have great quantitative agreement between predictions from modeling and experimental results, and we looked at that in great detail. But I think for the broader community to sort of adopt these methods, it will be helpful, to have modeling capabilities for that inverse problem, even if it's relatively simple in terms of the capabilities. So we've published a couple of papers in that direction. I think there's a lot more work that needs to be done, but I think you'd like to be able to simulate. So and I think the simulations are going to go beyond how to design a desired 3D architecture, but also to the question of how the actuators impose movements of that 3D architecture. So the whole thing, not just the fabrication approach, but a full set of multi-physics models, and those may also extend to understanding how the electronics and the radios operate in these 3D structures. It's multi-material, and you have to think about how the entire body of the robot is acting as an antenna, for example, if you want to do two-way wireless communication. So that's not, modeling is not our main emphasis. That is in my group. We're more of an experimental group, but in terms of the broader community, I think the field would benefit from models, that can be made available as open software for the broader community to leverage in the design of robots for the future in this size regime specifically.
Mm-hmm. Great. Maybe since it goes to end, I have a few questions for you. The first one, the interplay again between the material architecture, and here we have fabrication, maybe a characterization modeling. There are many things here, but mainly for the material architecture across different scale. What is the key factors, if you can pinpoint, that's very crucial in this design for that interplay between material architecture?
Yeah, I mean, I think coming back to a point that I made before is that the alignment of our fabrication approaches with the vast array of thin film growth and patterning techniques that have been developed over the last century or so turns out to be really important. So we can integrate shape memory polymers with shape memory alloys, with device grade semiconductor materials. We can build in light emitting devices, integrated circuits, and so on. And I think for multi-material structures, you want your overall fabrication schemes to be aligned with the state of the art, right? And so we can use materials deposited by physical vapor deposition, chemical vapor deposition, MBE, MOCVD, all of the latest and greatest and most powerful ALD techniques in thin film growth are immediately applicable, and we can leverage all of those. in a very straightforward way, and then not only depositing those materials but patterning them, each one a layer at a time, and in essentially perfect registration with one another, just using the kinds of lithographic techniques that exist in the semiconductor industry. So feature sizes well below a micron are very easy to achieve these days, and overlay registration also to precision at a very, very small fraction of a micron. So probably addressing any kind of conceivable need in micro robotic structures. So if that's your starting point, you're in a very good position to leverage diverse materials, heterogeneously integrated together with one another in ways that can achieve outcomes and address requirements of the robot ultimately. And that's probably the most powerful feature of what we're putting forward as some ideas for the robotics community more generally.
That's great. Maybe a quick question again about the using heterogeneous material. Maybe I want to ask you the right approach to combine different material combination in one structure.
Yeah, I mean, one way to do it is just deposit one layer after another. You can do that, and that's the foundations for how integrated circuits are built. But in some cases, certain of the materials will be incompatible with deposition conditions associated with other classes of materials that you might want to include in your overall structure. And so, we and now a number of other groups as well have addressed that limitation by the development of techniques in transfer printing. And so we use soft rubber stamps to lift these thin film material structures formed on one substrate, to lift them onto the surface of a soft stamp so that they can be delivered by printing process to another surface, another substrate. And that's a pretty simple concept, but it works extremely well. It's used in manufacturing, and it's being explored as an example for the development of micro LED based displays, a very hot area of development in the display industry. And so there you're taking extremely tiny light emitting diodes formed on a growth wafer, and then you're using transfer printing to move them from that wafer in high density arrays into sparse arrays on a target substrate, which might be a plate of glass or a sheet of plastic. And so that turns out to be an enabling manufacturing unit operation that avoids limitations associated with the inability to grow crystalline material on an amorphous substrate. So it's very, very difficult, almost impossible to grow the kinds of materials you need for high performance inorganic LEDs on a glass substrate. So you bypass that limitation by growing them on a preferred substrate, a crystalline wafer substrate, and then you release them from that substrate and print them using these soft stamps onto the device substrate, the substrate you want to build your display, glass or plastic as examples. And so that turns out to work extremely well. And you can leverage that kind of scheme also, to form these planar precursor structures for these micro robots that result from this kind of buckling pop-up process. So you can do very heterogeneous materials integration in that way. And as a result, for us, we demonstrate in these robots, we're including polymers. It's a polyimide sort of base or body for the robot. We have these shape memory alloys, metal alloys, integrated with ceramic. It's a thin glass coating. So those are fairly diverse materials. It's metals, it's polymers, it's ceramics. We don't have semiconductors in there, but we'd easily add those. We could include, transistors and LEDs, like whatever you want. But that kind of heterogeneity is probably, going to be required for any kind of robot that has sophisticated modes of operation. And I think, that this scheme can accommodate that diversity of materials pretty straightforward way.
Mm-hmm. So question left, the first one. What may be other open question and also expectation from this paper especially in micro robots design here? Is this scope? What are the expectations of this paper? And still open question.
Yeah, I mean, I guess, it's kind of, a set of ideas that we're trying to share with the community that we think might be valuable over time. I think we're pretty happy with the robots and their performance, but it's important to point out that they weren't designed to satisfy detailed technical requirements associated with a particular application. It's more of a kind of open-ended exploratory effort to see what's possible and to share ideas, like I said, with the community, with the hope and expectation that those ideas would be valuable to add to the broader toolkit of options in the development of microscale robots. But I mentioned, there's a limitation. You need direct kind of optical access in order to make the robots move. It'd be better to have onboard power. It'd be better to have a more efficient actuator that could deliver more force over a larger range of displacements. There's all kinds of opportunities for improvements. The robots are walking around, but they don't have separate limbs that can be actuated to manipulate objects, for example, which seems like it's probably something you would want to have ultimately. So it's a very much a starting point, many directions for new ideas and added technical sophistication. We're pretty happy as this kind of a still starting point, though.
Yeah, maybe last question. If you look to maybe down the road, what is the ultimate goal? You mentioned many features, but when you think about this insect we have in evolution, and we already have this background in the labs, and I think that's very interesting. I would like to ask you, what is really the key point here to go what we see like in the insects? Just what is the thing?
I think the actuator piece is the area that could benefit most strongly from new ideas or improvements. I think the control systems, if you consider integration of microelectronic components, I think that can be very sophisticated. Maybe not the most power efficient, in terms of thinking about biological inspiration, but still, in terms of function, I think the neural networks that you can achieve in silicon are quite powerful. It's really that actuator piece. I mean, I think the fabrication approaches look pretty good to me. I mean, not perfect, but that seems pretty good. I think actuator approaches, the shape memory alloys, as we discussed, works pretty well, but the range of motion is sort of limited, and the power efficiency is not great. Like, how do you create a muscle, that operates like those in the insect world? That would be hugely valuable. So I think that's an area, and I think the community kind of appreciates that more or less. I don't think this is new insight, but it's certainly just kind of a reinforcement of a general perception that I think is already out there.
Great. I don't know if you have any final words, maybe about paper, or maybe people listening to you, any final words like to say?
No, I just think this is a great area for research. It's certainly fun for us, to be active in this space, and there are plenty of there's plenty of room for creative people and great ideas, and I think it's a rapidly evolving field, and it'll be interesting to see where we are in 3 or 4 years.